So, welcome to this topic describing function analysis. As you can see, I have a PDF instead of a PPT made, and I will go through the PDF. This is an entire chapter from a book, and I will circulate this PDF also with you guys. But all these 31 pages you have to read. However, there are some important points which I would like to go through. So because I have not made a notes of this or like a PPT of this topic, because I guess one should read through the entire chapter, and there are several such points which might be missed when we go through a PPT. So these are like some the first two pages are like some introduction to the describing function. So you can see that the van der Pol equation is here again, and so this basically indicates that the describing function analysis is actually it is an analysis through which we come to understand about the limit cycle behavior of a nonlinear system. So when does a system would have this sort of a limit cycle behavior? So I think you already have understood that the limit cycle is basically, what does it indicate? It indicates that there is a periodic output due to some input appearing in the system, or the system response is such that it has some periodic output. So in case of any periodic input, we can also have an understanding that the output would be periodic in nature. However, this does not go on to say that for a sinusoidal input, so if you have a sinusoidal input like this, the output will also be a sinusoid. No, it is not so. That is true for a linear system. If the input is a sinusoid, output is also a sinusoid, and we have a gain and a phase shift. So a gain change happens and a phase shift happens, and we have the frequency response, which is the gain plot and the phase plot. So that we can obtain for a linear system, which are the Bore plots. However, in case of nonlinear systems, what happens is that when you give a input like this, which is a simple sinusoidal input, you can get a periodic output if there is existence of limit cycle in the system. If there is existence of limit cycle in the system, you will get some periodic output, but that periodic output may not be a pure sinusoid. So if it is not a pure sinusoid, then what it is? We know that from our Fourier system, Fourier series knowledge, we know that any system, any signal which is a periodic signal is basically a composition of sinusoidal signals of different frequencies. Okay, so all these harmonics come and become present in that signal. So this is just introduction part mainly, so you can read all through this, you have a brief understanding. Now some main points I have highlighted in the PDF. So the first thing is, which sort of systems can we actually analyze for limit cycles using the describing function method. So what do we do actually in the describing function method? Very briefly, in one line, what we can say is that the input, which is a sinusoid, and it is resulting into a periodic signal, we approximate that periodic signal with a sinusoid of the fundamental frequency only. So there are a lot of other sinusoids also, but we assume that the amplitude of those sinusoidal signals are very less. This is a fundamental assumption of the limit of the describing function method, of the describing function analysis. So if we are able to do so, then we can go ahead and formulate the describing function function analysis for a particular nonlinear system. But when can we do so? When can we approximate, or when can we approximate the periodic output of a nonlinearity with only the fundamental harmonics? So you look at this figure 5.4. Here the nonlinearity is here, and then there is a linear element. So when we have a form like this, then what happens, basically you can approximate that the output of this nonlinearity, which is a series of sinusoids, passes through this linear element, and as we know that any linear system is basically a low pass filter. So we can assume that only the fundamental passes out of this system and the other frequencies are absorbed into this system. So they are filtered out by this system. So only the fundamental passes out. So here again you get the fundamental, okay, and this xt is also the fundamental frequency. So in this configuration, if you have any system, then you can actually analyze the system with describing function method. What is this form? This form is, you can see, very simple. Previously we are very accustomed with only the linear system in the forward loop and a unity feedback. Here a nonlinear element is also attached with the linear element in the forward loop. So you can assume that this may be a actuator or a controller nonlinearity, something like that, or maybe the actual system can be broken down into a linear part and a nonlinear part, and they together are combined in this manner. So whatever be it, in whatever way you can arise at this type of configuration, if you arise at this type of a configuration, then you would be able to implement the describing function method. This is also another sort of configuration. Here at the input side and as well as the output side, even in the feedback you can have linear systems or linear elements, but there is a central nonlinearity. We are analyzing this nonlinearity, okay, and here wt is a sinusoid, ut is also a series of sinusoids, but we can assume that the entire system, in the entire system, the output, this yt, is only the fundamental. So we can analyze this nonlinearity with a describing function method. Now what is the describing function method? Let us go into that. So here that this is described what I was saying about filtering out of the higher frequencies. So you see linear element has low pass properties, all these things are written here. So this is so there are some basic assumptions as we go on to formulate the describing function. So the assumption is that there is only a single nonlinear element. This means that either there is only a single nonlinear element or all the nonlinear elements in the loop are clubbed together to form a single nonlinear element. The nonlinear component is time invariant. It should not change with time. Corresponding to the sinusoidal input, only the fundamental component in the output has to be considered. This we already understood. The nonlinearity is odd. This is assumption is taken because to simplify the Fourier series calculation basically. So if you have odd nonlinearity, then the output will not have any that mean component A0 which comes in the Fourier series. So you see that the fourth assumption, plot of the nonlinearity function between the input and output is symmetric about the origin. This is for simplicity, so that the static term, which is the A0 term in the Fourier expansion, can be neglected. Okay. Actually, all the common nonlinearities that we have discussed in the before satisfy this assumption. So this is some basic definitions of Fourier coefficients if you have forgotten. So this is the Fourier coefficients, and this is what actually we would do. So when we actually get the describing function, so then we would be able to replace the nonlinearity with the describing function. What is this describing function? This is basically a ratio. We have the definition here. Let me see. Yes, here. So what is the describing function? It is the complex ratio of the fundamental component of the nonlinear element by the input sinusoid. So the nonlinear element is producing the periodic output. You take only the fundamental component of that. That fundamental component is this. So you have this fundamental component is this A1 cos omega t plus B1 sin omega t, which will give you m sin omega t plus phi. So this is m as a so your a and omega. What are a and omega? A and omega are your x is basically a sin omega t. So it was written somewhere a the input signal, the input sinusoid is a sin omega t. Due to that input signal a sin omega t, you are getting the output in this form. Hence you are saying that m, magnitude m, is a function of that a and omega. If you change your a and omega, you will get a different m. Similarly, your phi a and omega. If you change your phi, you will get a different. If you change your a and omega, you will get a different phi. So your describing function is the complex ratio of the fundamental component, which is the output, this fundamental component, divided by the input sinusoid. Input sinusoid is a sin omega t, right? So here you see that it is a e to the power of j omega t. In this way we have written the input sinusoid, and this is the output sinusoid, you can say output signal. So m e to the power of j omega t plus phi. So m sin omega t plus phi. So it is written as m e j to the power of omega t plus phi by a e to the power of j omega t, and that would be giving you m by a e to the power of j phi. So this is like this 1 by a b1 plus j a1. So this is the describing function. So this is basically a ratio of the input to output, a simple linear ratio. It is like a linear ratio of the output to the input. Hence the nonlinearity that we had in the time domain, when we come to the frequency domain, it gets transferred to a linear a linear nature. We get this describing function directly transfers the amplitude a to m using a ratio, and the phi also we can calculate using the describing functions uh, expression. So this is how actually the nonlinear element in presence of the sinusoidal input. So with other inputs this will not work. Okay. So in presence of sinusoidal input, it can be treated as if it were a linear element with frequency response Na omega. This is an extension to the notion of the frequency response in linear systems. But it differs in the fact that the describing function here also depends on the input amplitude A. So the gain is also dependent on the input amplitude A. In linear case, this was not so. In linear case, the gain was not dependent on the input amplitude. That here it is dependent on the input amplitude also. That is why it is called quasi-linearization. So in the case when the nonlinearity is single valued, the describing function is real and independent of the input frequency omega. When the nonlinearity is single valued, so then the frequency then the describing function is real and independent of the input frequency omega. So you saw that Na omega can be, is basically a function of A and omega both, but in case of single valued nonlinearities, it will not be a function of omega, it will only be a function of A. And how to compute? There are several ways. Analytical computation, when you already know the function, then you know what is W, and then you can calculate the Fourier series for W. So you can calculate the A1 and B1. Basically A1 and B1 is what we need to calculate in the Fourier series, and then we get the describing function. Numerical integration from the plots and graphs and tables, if you have the input output relationship, then you can do numerical integration. Experimental evaluation, so this is same as doing the frequency response analysis of a linear system. So we can excite the nonlinearity with sinusoidal inputs of known amplitude and frequency and determine what is the output we are getting, and from that we can experimentally determine the describing function. So the most important difference here is that in a particular frequency we have to also vary the amplitudes of the input sinusoid. Okay, so in linear case we could give a unit sinusoid we can give, and we can simply keep on varying the frequency. But here at each frequency we have to also check for different amplitudes. So these are now after all this description about what basically is the describing function, we have to compute the describing function also. So there are some examples given and you can practice these examples. This is from how you will have to calculate describing functions. So first is one where you know the nonlinearity. So with the help of that you can calculate A1 and B1 and you will get your describing function. So the describing function, after these calculations you will get, this is the describing function. So these are basically all integrations. So I am not so comfortable in explaining integrations also, but this is just a math, just integration. So you should like read through it and also practice it on hand so that you can do the integration by yourself also. So this is done here, so you should also practice it. Other common nonlinearities in the control systems, we would have saturation, then on off nonlinearity, which is relay, dead zone, etc. So for all these we can calculate the describing function also. So the saturation nonlinearity, we see that this is a saturation nonlinearity if we are passing a sinusoid and we get this output basically where the top is chopped off, right? So this type of output we get, and we can calculate the WT. The WT is like this. So you verify that it is like this between 0 to gamma, when omega t is between 0 to gamma, we are having the linear range, and then we are chopping it off basically till this part. So from gamma to pi by 2, that it is simply Ka. Okay, and this is actually symmetrical quarter, like it has been taken up to pi by 2, because after that it is becoming symmetrical. So only till this part we have tried to formulate what exactly is the equation. So after that it is just repetition, the integration will just be repetition. So so this is, you see the symmetry over 4 quarters of a period. So the B1 is basically 4 by pi integration 0 to pi by 2 omega t sin omega t d omega t, and then you evaluate, you put down what is omega t. So from 0 to gamma and from gamma to pi by 2, there are two different functions, and then you evaluate, you get this expression. And when you get this expression, then your describing function is nothing but b1 by a. Here you see that a1 term is not there. Okay, a1 is 0. So na, which was 1 by a, b1 plus j a1, that a1 part is not there. So b1 by a, and that is like this. It is na, and we can also have the normalized describing function by taking this k in the denominator, na by k. So what was that k? That k was your this slope of the saturation. So the saturation slope could be changing, that's why we can have a normalized describing function. So that is the thing. So you see that we can observe some features of this describing function. This na will be equals to k, completely equal to k, if the input amplitude is in the linearity range. So it is obvious that it is simply k. Na decreases as the input amplitude increases, there is no phase shift. So all these are quite obvious observations and explained also in these paragraphs. And there is a like derivation from this describing function. From the describing function of the saturation, we can actually derive the describing function of a relay. Relay will be in the case when your k becomes infinity and a becomes 0. A is the time till which it was linear, right? So a is 0. Let us see what is a here. K was the slope, a is the time till it is linear. So a becomes 0, k becomes infinity, and when you make that in this particular expression, you will get na as 4m by pi a. Your b1 will become 4m by pi, na will become 4m by pi a. So you can remember this one. Describing function of a relay and nonlinearity is very simple to remember, 4m by pi a. The normalized describing function are plotted, so you can see the different plots you are also having. So these plots can also be remembered. And dead zone nonlinearity, in the dead zone nonlinearity, you see that there is a period where it is 0. So you have to there is a period where it is 0 from 0 to gamma, and from gamma to pi by 2 it is sinusoid with a phase shift, and then you can compute it, and this is your na, what is your na coming up. Backlash is also very interesting. So all these are basically, you have to compute what is your wt first by looking at the these graphs. So graphically you have to see what is your wt, and then you have to break down your wt into symmetrical parts and integrate and evaluate a function in each range, and then integrate. So all these different steps are there for calculation of the uh, describing function. In case of backlash, you see there is also an angle coming up. So previously all were without the angle, but in backlash we also have a phase shift. So you see the amplitude of describing function for backlash, b by a plot, and you have a b by a plot, the phase angle of the this thing, phase angle of the describing function. The phase angle is also there. So both plots are there. Now after we calculate the describing function, after we obtain the describing function, what to do with it? We have obtained a describing function. Yes, with that we can predict the output. Approximately we can predict the output when we are exciting the system with a sinusoid. That is one thing. But the important feature, the qualitative feature that appears in the system is the limit cycle. So when we have that limit cycle in the system now, because we are having periodic behavior in the system, so there is a limit cycle. What we have to ascertain is that how many limit cycles would be there and what are the type of limit cycle, whether they are stable limit cycle or unstable limit cycle. So these are the things we need to ascertain. The describing function analysis helps us to do that. We take the help of the Nyquist criteria and its extension in this case. So briefly remember Nyquist criteria. In Nyquist criteria we have to plot this GP-HP. This we have to plot and we have to see the encirclement of the point -1 in the in the P plane, the Nyquist plane, the complex plane, real and imaginary plane. So there we have to see the encirclement of the point -10. Okay, this we have to see, and this we already know the unstable poles of the unstable poles of delta P. So delta P is the loop transfer function and Z is the unstable zeros of the closed loop system. So Z is the number of zeros of the delta P, and delta P is the this is the characteristic equation of the closed loop system. So this Z becomes the number of unstable poles of the closed loop system. So that is how we ascertain the stability of the closed loop system using Nyquist criteria. But we extend that criteria here. So that extension we can give a simple extension. If we have a gain associated with this GP-HP, a gain K, then basically what we have the characteristic equation as this. So we have to look for encirclements of -1 by K. So if this is true, then if we have a system like this, where you see this is the gain K, instead of K it is NA omega, the describing function. So what we have to look, we have to see actually the characteristic equation becomes like this, and we have to see the encirclement of Gj omega of the plot n minus n1 by na omega, not just -1 by K. This is also a plot, this is also a curve in the complex plane. This is also a curve in the complex plane. We have to see the encirclement of Gj omega of this curve. How many times this has encircled this curve? Okay, this we have to see. So that is the thing. So here basically you see that basically we have to see where these two curves actually intersect. These points we have to note down, because that is the places where we will have the Gj omega Na omega being -1. From there only this equation has come, right? So whenever Gj omega Na omega becomes -1, that is the critical situation. There the periodic solutions will exist. There the periodic solutions will exist. So that we are evaluating by looking at the intersections of these two curves. So in those points of intersection we would have limit cycles. If we find that there are no solutions, no intersections, then there is no limit cycle. There is no limit cycle. So we have to actually find the intersection points. So if we have intersection points, then there exist limit cycles, and the value of a and omega correspond to the intersection point of the solutions. So at that intersection point we have to find out what is the a and omega. That is the values of your a and omega or the values of the excitation a and omega for which we will have the limit cycle. For all inputs we will not have limit cycle. For these input which is in that particular intersection point having the values a and omega, we will have the limit cycle. If the curves intersect n times, then there are n possible limit cycles. Which one is actually reached depends on initial conditions. The amplitude of the limit cycle, the value of a is ak, and the value of a corresponding to the point k on the 1 by na curve. So what is the 2 points intersect at a point k. So 5.23 they intersect at this point k. So we have to check the value of a. So it is ak and the value of omega, which is omega k. So these two we have to check. So the amplitude of the limit cycle would be ak, and the amplitude of the and the frequency of the limit cycle would be omega k. So this is what it is saying. So it is it was not the amplitude of the input. The amplitude of the limit cycle is ak, and the frequency of the limit cycle is omega k. Yeah, note that for single valued nonlinearities n is real. So we already calculated for single valued nonlinearities which are the saturation on of these nonlinearities. So we calculated that the n is real only, there is no complex part. So since it is real, the minus 1 by n will also be the real line. It will be simply the real line, simply the real axis, nothing else. So we have to only find out the intersection point of gg omega with the real axis. Now we have to remember that this describing function method only predicts the limit cycle. Whether the limit cycle actually exists or not, we have to actually do a computer based simulation. So just before going to the computer based simulation, we can do this analysis of it. That is the thing. Now if we have frequency dependent describing functions, then we have a family of curves like this for different frequencies. Normally sometimes what we do, we directly plot gj omega na omega. Directly we plot gj omega na omega and see where it passes the point minus a1 0 in the complex plane. So there the limit cycle would exist, and we evaluate find out the value of a and omega at that point. Now the most important part, what do we do about the stability of the limit cycles? So we have found that there are some limit cycles, but whether the limit cycle is stable or not, can we decide that? Yes, we can decide. So for that, what we are actually seeing here, you see this graph here, this is the minus 1 by na omega line, and this is the gj omega line. So these are intersecting at 2 points L1 and L2. So if the curve, if this curve is encircled by gj omega, then it is the place where you are actually growing, right? So you see you are actually, that is the key, and that is the point where you are unstable in this region. In this region you are unstable. We are not saying whether your limit cycle is unstable. In this region you are unstable. That means you see here actually now So here your A is increasing from in this direction. Okay, your A is increasing in this direction. Now let us see here the stability of the point L1. Let us see. So if we have a slight disturbance, so how do we ascertain stability? We first have to give a slight disturbance and see whether we are coming back to that point or not. So when we give a slight disturbance, the amplitude of the input to the nonlinear element is slightly increased, that is true, and the system operating point is moved from L1 to L1 dash. This point it is coming. Now here this point is actually encircled by the curve Gj omega. According to the Nyquist criteria, the system at this operating point is unstable. The system at this operating point is unstable. That means its amplitudes will grow. The amplitude of the system signals will grow, increase. So in which direction it will move? So the amplitude is increasing in this direction, so it will move in this direction. So it is further going away from the limit cycle. So if we have a slight disturbance from the limit cycle, since this point is this region is unstable, it will further grow. The amplitude will further grow and it will further move away from this limit cycle. If it is in this direction, if the perturbation is in this direction, then this is stable. That means the amplitude A will reduce, right? So you see here L1 double dashed. So on the other hand, if the system is disturbed so that the amplitude A is decreased, move to the point L1 double dash, then A will continue to decrease. A will continue to decrease because this point it is stable, so it will continue to decrease, and that's why it will move away again from this limit cycle, from this L1 point, which indicates a limit cycle. Hence that the limit cycle L1 will not be stable. Actually the limit cycle L1 will not be stable, but in this point L2, what is the case? You see in L2, if you have a slight disturbance in this direction, then since this is unstable part, the A will increase. That means you did further go in this direction. So if you move away from this direction, it will again go in this direction. In this region, what is happening? If you go in this direction a bit, then since this is stable region, this will try to decrease the magnitude A and it will push this in this direction. So from this direction it is pushed this side, this direction is pushed this side. So this L2 will be a stable equilibrium. So the criteria is stated here. Each intersection point of the curve Gj omega and the curve 1 minus 1 by n a omega, it will be, corresponds to a limit cycle if the points near the intersection and along increasing a side of the curve are not encircled by the curve Gj omega, then the corresponding limit cycle is stable. Okay, so whatever we have discussed, that is mentioned in this one single line, but you have to remember what is the actual thing. So because you will not be asked this statement, but you will be normally given some plots like this and you will be asked to ascertain the stable or the unstable limit cycles and why those are stable or unstable. So after that, the reliability of this analysis, so it is quite reliable. It has been found out heuristically, it has been found out that we can rely, but there is of course some inaccuracies possible. What sort of inaccuracy? The amplitude and frequency of the predicted limit cycle are not accurate. So the amplitude and frequency of the predicted limit cycle are not accurate. The predicted limit cycle does not actually exist. Predicted limit cycle does not actually exist. This might also be the situation. Existing limit cycle is not predicted. So an existing limit cycle which may actually exist is not predicted by this method. So all these different sorts of anomalies may appear actually. Also, this filtering hypothesis is a very critical hypothesis in the describing function method, but it might not actually hold true always, because the linear system, that the filtering of that linear system is critical actually in this hypothesis. Graphical conditions. So if we have a very critical sort of a graph like this, so close limit cycles, so basically due to the harmonic presence, this might actually be not even touching the gj omega curve. The actual frequency response curve may not actually be touching. So in reality there might not be any such limit cycles also. So all these different things are there. So this is an overview of describing function method. I suggest you to go through this document, this chapter. So you read it slowly and you will come to understand what is there in it. So normally for numericals you will be asked to evaluate describing functions for different nonlinearities. The examples are given here. More or less it will come nearby only. So you should understand how to actually evaluate describing functions and how to predict the stability of the limit cycle using describing function method. These two are what is there for the purpose of your numericals and application of describing function analysis. So that is all. So thank you for your attention.